different layers of liquid will take it. So this is the ground. So let the river, the flow of river water will take it. So let's go for water will have viscosity. So when I go and compare the different layers, so if you check there's a river bed, and what is this? River flowing. We know at the river bed, what is the state of the liquid? With almost will be at rest, no? And the topmost layer of the river, this is topmost layer of river. Fine. So the topmost layer of river waterpan will have the maximum speed. And as you get into the as the depth increases, so then velocity of the layers of the river which is flowing will decrease, and the layer which is at the river bed, which is in contact with the ground, will be almost at rest or will be at rest here. Why the different layers are having different liquid? The reason is because of viscosity. So what is the viscosity? How you to define viscosity, like, and all? How to define viscosity, that one? So when a liquid is in motion, so layers what happen will execute a mutual resistive force on each other. And that particular resistive force is what we can call like a viscosity here. So when do this viscosity will come? Only when there is a motion. When the liquid is at rest, it will not come into picture. A liquid which is in motion, the different layers will exert force on the adjacent layers, and they will try to oppose the relative motion between the layers. Just similar to the friction. So how to define viscosity now? So there'll be like a opposition to the relative motion between the layers, and that particular opposition is what we should call a force. That is called like a viscous force here. So shall we define any basic definition, or just okay theoretical idea? Yes, we need some small definition. So what do you mean by viscosity? Okay, fine. Just wait. Okay, now we'll define viscosity first, then I'll come back to this one here. So it's like it is a the resistance offered by adjacent layers to oppose relative motion between them. Okay, now so it's a measure of resistance offered by the adjacent layer to oppose relative motion between them. There's a one thing. So now, so what do that viscosity will do? It will oppose relative motion between the layers, and due to that, what happens? There'll be viscous drag will be there. So same thing. Now let me give a number. So there's a layer 1, layer 2, layer 3, layer 4, layer 5. Now one will have velocity v1. Different layers will have and here v1, v2, v3, v4, v5. Fine. This will be now v1 greater than v2. Tell me like what is the velocity of 1 with respect to 2 will be. So V12 will be in this direction. So how the viscous drag on this layer will be, it will be opposite to this. I'll put F12. Similarly, V21 in what direction will be? V21 will be in this direction. I have to show layers, no? Okay, it'll come here. Then in what direction the F21? Opposite to that. So here, F21. Similarly, V23 will be in this direction. So then how the viscous drag? F23. V32, in what direction it will be? V32 will be in this direction. Sorry, it will be. Like this we can go for. So they will exert force mutually to oppose relative motion between the layers here. Now you can see this. What is the velocity of one greater than two? So what layer two will do? Layer two will try to decrease the velocity of layer one. Layer two is having less velocity than one. So what this viscous drag will do will try to increase the velocity of layer two. So what they do, the viscous drag will act to oppose relative motion between the layers. So due to the viscous force acts to oppose relative motion between the layers. Fine. So there's a one condition what we can put here. Okay, next question comes. This viscous drag depends on what all? According to the Newton's formula, what he proposed is the viscous drag is directly proportional to area of contact. Let me put it, this one, viscous drag area of contact between layers. It is directly proportional to relative velocity between layers and inversely proportional to perpendicular distance between layers. Okay, like this is what he has proposed here. So this viscous drag, the formula is what? I'll suggest like this, eta A dV by dr. What is dV dr? So we have to put, all of you able to understand this one? Similar to like a friction only, but here it depends on area of contact. Area of contact between the layers. And it always acts to oppose relative motion between the layers. And it's a natural property of a fluid. The different layers of a liquid or pen, they'll exert force on the adjacent layers to oppose relative motion between them. Okay, getting this one? Okay, now let's try to understand this formula once again. Okay, this is called like a velocity profile. We show so if this is having a velocity, say v plus delta v, and this is having a velocity v. And what is dr? Dr will be like this. Fine. So the area of contact. So what I'm showing is velocity profile. This will be. So then in what direction the viscous drag should act on this? So it should be F like this and the F should be like this. See. The force exerted by this layer on this layer on this one. So what is V plus dV? This layer is having more speed than this one. This layer is having a more speed than, and what is the dr? Perpendicular distance measured between layers, because I had to show that dr, no, dr will be in this direction. Sir, will there be any viscous drag on these two? Yes, it will be there. So like that, we can go for all the things. So if you check the velocity profile, so what do this length of arrows will indicate the speed of the layers. And layer which is in contact with the ground will be almost at rest. It will have zero velocity. Why do that negative sign? Because it will act to oppose relative motion. What is the velocity of layer 1 with respect to layer 2 towards right? So it will act opposite to this. By velocity of layer 2 with respect to 1 will be towards left. So viscous drag will act here. Like that, I think better you imagine pages of notebook. Different pages, all pages are moving in the same direction in same direction with a different speed. Then there'll be viscous drag between each pair of a page. So still we are not able to understand. So I think this layer, some of you are getting confusion. I'll show a diagram like this. This will be a better diagram. The layer 1, layer 2, layer 3. This is having velocity V1. I'll give some very good diagram so that it will be easy for you to this one. Uh, it is having velocity V2, V3. I'll put a condition. It can happen V1 greater than V2 greater than V3. Okay, tell me like how the viscous drag I have to show on the layers. F12 should be like this. So where you have to show, you have to show it here. Is justified now? Then F2 greater, V2 greater than V1. So is it okay now? F21, F23. Similarly here. So on the layer 2, you check it. F21 and F23, both are acting. Okay, now let's take this is A, this is B, this is C. Okay, let's write F12. What is F12? Eta, area of contact, let it be same for both. Now what shall I write dV now? V1 minus V2 by E. Similarly, what is F23? You'll write it eta A. I'll bring eta. Eta is called as constant. It is for different liquids, it will be different, and for a given liquid, it will be almost, you can say, constant, coefficient of viscosity. Now eta. What shall I write here? It should be V2 minus V3. Correct. It will be F23 will be distance between layers. It will act to oppose relative motion. V12 towards right. Bring F12 opposite to that. Okay, these are the layers I'm taking that one. So there's a layer 1. Actually, the distance between layers is A. Some of you are getting confusion, sir, how you are. Okay, I'll come once again. You can see now. What is the distance between layer 1 and layer 2? Layer 1 and layer 2. I'll give better diagram. So most of you are unable to understand anything. No. Okay, let's come. Okay, this is a layer 1. Let me show at least a thick line, the same thing. Okay, this is a layer 2. Sir, they are not in contact. Actually, they should be in contact here. That's why it's a better to show this one. In the books, they have shown thick lines, but usually this will be the method. If I show gap again, you'll get confused. Once again, I'm coming because this is what you have to understand. So this is what you call layer 1 velocity, V2, V3. Is it okay now? So let's take this one. What is the separation between them? A, this is B. Okay, let's come here. Now I'll put a condition V1 greater than V2, V3. Now V1 greater than V2. So what this layer 2 will do? Will oppose the motion. So therefore F12. Similarly, on this layer, you have to show F21 like this. So here it's a practice of showing it here. This rather than here, you just show it here. No, same thing happens here now. V2 greater than V3. So therefore there'll be a viscous drag. How do it will come? It will be like this, F23. Or here you have to show it F32. So any relation, any reason for that? V12 will be in this direction. Look at here now. So therefore opposite to V12, F12 you have to look at. Now how the V21 will be like this. So opposite to that F21. Then what do we get? V23 in what direction will be? V23 will be like this. I'll show it here. Velocity of layer 2 with respect to 3, opposite to that. Similarly, V32 will be in this direction. Sorry, V32 will be in this direction. Getting the idea now? Just the viscous drag will act opposite to left. So let's come for this one. So what is the F12 formula? Eta A V12 by what is the separation between them? F23 or F32. What will be that? F23 or F32 should be eta A V23 by B. So now you look at this layer. This layer, what will happen? Will experience a force due to topmost layer and also the bottom layer, the below layer. This one. So if you layer 2, what happen? Will experience force due to this. So there's a one generalized method is what we are trying to show here. It's a similar to friction block, 3 blocks better. Only thing is that this area of contact we have brought it. Friction opposes relative motion. Similar viscous drag also opposes relative motion. Now this is called like a coefficient of viscosity. What can be unit for this? We'll search for unit for that one. Coefficient of viscosity. So F is equal to eta equal to F into dr A by dv. What can be? We know dimensions. So what can be this eta? Force will be Newton. Force will be, we'll go for dimensions. So dimensions of force will be m, l, t minus 2. dr will be L1. Area will be L square. Velocity will be L t minus 1. So what do we get? M L minus 2 t minus 1. Okay, fine. This is, so what can be, what is the unit you can suggest finally? Pascal. Pascal per second. See, or we'll do one thing. Instead of doing all this, this will be the dimensions formula of the quotient of viscosity, because I had to L minus 1, no? L minus 1, yeah. This will be the dimensions formula of the quotient of viscosity. Come for here. Now, force by area will become Pascal, no? And distance by time. Time will come, so Pascal second. So what can be unit for quotient of viscosity? It should be Pascal second here. Unit for quotient of viscosity is Pascal second. So how do we write that? Is Newton per meter square seconds will write it as, no? Newton meter, so Newton per meter square will be the force, like a pressure. Second it will come, so Newton meter square second. This will be the Pascal. This is what we'll call this is a Poiseuille. SI unit Pascal second. It is a, or you can also call it as Poiseuille. Poiseuille. There's also SI unit. So the quotient of viscosity, what happened, will express in terms of Poiseuille, that one. Rather than this, the more popular is the poise. The more popular is the poise, that one. This is the dimensions. This is a SI unit. Viscosity Pascal second or Poiseuille. Either of this one. So CGS unit is what? Poise. And all our new formulas, you can see like it is there in terms of poise only. So poise is what? 1/10 of Poiseuille. Poise is what? 1/10 of. So therefore, the Poiseuille is also called as decapoise. So what you can call this one? Poiseuille, one Poiseuille. You can call that as decapoise. Later on the numerical, okay, we'll get an idea. So these are about the units, what we can put it here. So these are viscous drag. Okay, let's take some small examples. Poiseuille, we don't have any symbol, or you can, we don't have any symbol specific, that one. We don't have any symbol. Okay, no, the biggest problem is, okay, viscosity we brought. How to check that streamline turbulent flow? There's a big headache even till date. So there should be some method, streamline turbulent.